Go ahead and start the recording.
It started.
Okay. All right. Hi, everyone. Welcome to our presentation. Our group's project is on wireless information and power transfer using beamforming. Our project owner and sponsor is Professor Chakravarti. Each of our team members is myself, Aaron Bennett, Shai Johnson, Orion Williams, and Braden Tucker, with additional help from Professor Yadav. For this, we're going to start off going over the project summary, just going over the overview of the whole project, the goals we had for it, and the current completion status. We'll take a look at the planning management of it and the resources we use. We'll go a little bit into the project, analyze what we've done and the development steps we took to get there, and take a look at the results, and then go over our reflections at the end. So our project is based on researching different ways of optimizing energy and information transfer using full duplex relaying. Our motivation was to use like an access point to communicate data and energy to a relay, and have this relay use specifically beamforming to send focus signals to specific places and hosts. And doing this, we decided to go forward and use amplified forward mode of relaying rather than decoding forward. And our final deliverable is a Matlab prototype, which we'll see at the end, and various equations. And with the addition of our new team member, Braden, we also added on a bit to our project, which is adding in an eavesdropper. So that's on the network, and we have a jammer sending a signal to where the eavesdropper is present. And our summary is the same as before. The goals of this is to specifically optimize wireless information transfer energy harvesting when we know that there's an eavesdropper on the network, and have like a jamming signal sent to that eavesdropper. Our completion status is that we've completed the equations for the information transfer and energy harvesting portion, and we have the initial Matlab simulation done for the optimization, but we still need a bit more time to fully optimize it.
For our planning and management overview, we utilize the project management cycle, starting with initiation that came when we were picking our projects from the form of our capstone class. And then the planning was occurring when we were setting out our meeting times and when we were going to perform certain actions. Our execution is being displayed through our presentations, our milestones, and the monitoring and controlling comes into place when we have adjusted our project over time, as we've started with multiple different equations and we have molded them to better suit our project. And then the closure comes with our final presentation to the IAB board, which is now. All right, so our project plan, what we have added to the project plan is C-Day participation. We were able to participate and present our project at the capstone day at the Marietta campus. And then we have the IAB presentation, which is on the 4th. And then our activity log is used instead of the Gantt chart to keep track of our meetings and hours. Our resources and materials that were used, we utilize a IEEE standards for beamforming and wireless information and power transfer. We utilize Matlab for programming and the IEEE research papers on the following topics, which are beamforming, wireless information and power transfer, and jamming signals. And we utilize draw.io for system diagrams, and we also have we also utilize help from our project sponsor and Dr. Yadav.
For our project analysis, for our first milestone, we started a research of information transfer and energy harvesting. we thought of our initial problem statement and we created our initial motivation. By milestone 2, we began work on our problem statement. We got a new member, Braden, and we added in a jammer and an eavesdropper to our motivation. And we also began work on the framework for our paper. And by milestone 3, we had finished the equations for energy harvesting and information transfer, and we've completed most of our paper, and we have our results all said and done.
These next few slides are going to show some changes that we made along the way through this project, from changing our problem formulation, different equations, just overall there's not a published paper on our topic yet. So there was definitely a learning curve at the beginning. Go ahead, Aaron. This is another change that we made. So our main goal of this project is to maximize the capacity of our user while minimizing the capacity of the eavesdropper. So we want to maximize the information received at the user and minimize the information that the eavesdropper can receive. Here we're still showing some different changes. This was some of our handwritten equations from the beginning. You'll see more of the final equations later in the slideshow. Here, this shows the energy harvesting equations. They are still the same. We are considering that the energy harvested in relay 1 and energy harvested in relay 2, as shown here. The relay 2 is our jammer, so we're considering them to be equal. So the total energy harvested is just 2 times the energy harvested in one of our relays. And this is some of our problem formulation. It has changed some too, but the overall idea is still the same. Wanting to maximize the capacity of our user while minimizing the capacity of our eavesdropper. And at the bottom there, even our timing analysis changed. At the beginning, we considered just 2 different time frames, the energy harvesting and information transfer. And our new timing analysis has 3 different time frames. We changed alpha to tau just to make it more consistent with the rest of our project. So tau times t is our energy harvested at our relays, and 1 minus tau times t divided by 2 is our information transfer. And then also 1 minus tau times t divided by 2 is also information transfer. It's just in another time slot. This is some of our equations for coming up with the capacity of our eavesdropper. And there's really a lot of variables here. You can see CE is the capacity of the eavesdropper. So it's the only thing that changed here was our time slot, the 1 minus tau t, and then log 2 of 1 plus the 2 different variables there, and the variables are written right below it, which is just a power at our relays times different channels, power at our jammer times a channel with the beamforming aspect divided by the noise. Here is our problem statement. Of course, like I said, we want to maximize the capacity of our user, and we have some different design variables there. So in our problem statement, we want to simplify it down as much as we can to where we have as few as possible design variables and constraints.
Okay, so now we'll go ahead and show off the paper. Go ahead and get that out. Can everyone see?
Yeah, we can see you.
Okay, so this is the paper that we've drafted up until this point. You can see, start off, we have our executive summary, kind of background on it, and of course all of this will be available for download for you as well. But go ahead and take us down. So here we have the section on our abstract, introduction, section on beamforming here, which gives us a background on that, a written write-up of our problem statement, a little bit on full duplex relaying with a dual antenna, and finally, our actual equations in a better format, more readable format. So here we can see, explain exactly why we use like energy harvesting, how we're using information transfer, and then getting started on our actual problem statement. All right, so from here, I think it would be good to show some of our Matlab results and a little bit about the code and how we got there.
All right, can you see my screen?
Yes, we can see.
All right, so our MATLAB code, first, we just wanted to start off declaring some global variables that we will use across our different code files. Then we get into declaring some variables. Our T, which is just the time takes to transmit information from the access point to the user, is 1. We have some different constraints here that we'll use later in our code. Our power harvested at the relay is 15 times 10 to the negative 3, and our max would be 20 times 10 to the negative 3. We do have dual antennas, so our number of antennas is 2. And then here's where later we're going to make some changes in our code. Right now we have set distances between our access point and relay and our relays to the user and jammer to the user or eavesdropper. We're going to change this so it becomes a random value. That way we can get better results depending on the distances. The distances is how we came up with our channels. So we have the channel from AP to relay, or access point to relay, access point to jammer, access point to user, and access point to our eavesdropper. Our channels from our relay to user, eavesdropper, and jammer from user to eavesdropper. It's a little different because we have the beam forming aspect in here. Our bandwidth is 10 to the 6th. And so getting into our actual code here, we want to find the best or the optimal value for tau. So we have a for loop calculating different values of tau for our scenario. And here we're using fmincon with nonlinear constraints to calculate the max value of our capacity. Going into the max file, you can see here our F is our formula that was shown in the paper. So fmincon usually calculates the minimum values. So we had to put a negative sign out front, so then it calculates the max for us. Our nonlinear constraints are shown here. They're the same that are in the paper as well. And FMincon calculates these and finds the best optimal values for that tau value. So at this time, we have it set to where it runs for one iteration. And the thing we're going to be changing again soon is we're adding more loops to it, so we can get it running for multiple iterations at a time, like 1,000, 10,000, 100,000, whichever we choose to do, just so we get the best optimal values as a whole. All right, Aaron.
All right, everyone hear me? And now for our reflection. This task posed a ton of challenge for us as a group, and some of our main challenges just came from understanding wireless information transfer and energy harvesting. There was a lot that our group didn't understand, and a lot that we had to research and find out in the beginning. And as a team, we overcame it. We met with our professor, and with his guidance, we managed to get a decent paper out, and as well as get our Matlab results all good. And with that, I think that's everything. We'll go ahead and end the recording here.